In this talk, we will discuss some MCQs related to continuous functions. So, before going to take MCQs, let us recall that some definitions which we have already studied and properties. So, as you know that if f is a function from a metric space x to another metric space y, then this function is called continuous at a point x naught if for every epsilon positive there exists a delta greater than 0. So that is to say this epsilon is depending on epsilon. So this delta is depending on epsilon such that the image of the function f of the ball with center at x naught and radius delta contained in the ball whose center is f of x naught and radius epsilon. So that was the definition of a continuous function. So keep this in mind. For every epsilon positive there exists a delta such that the image of the open ball with center at x naught and radius delta contained in the open sphere with center at f of x naught and radius epsilon. Okay, so this was that, and then we have seen several examples. I am not going to give all these definitions again, and we know that the function is bounded if mod of f of x is less than or equal to m. And then we gave several characterizations. So here there are several characterizations, and that we can write in the form of a so here are the several characterizations. So let me write here is so this is the main result which so f is a continuous function on x. Okay, it is equivalent to say that for each x in x, if you have a sequence xn in x such that xn converges to x, implies that f of xn converges to f of x. Okay, so this is very important. And then the inverse image of open set is open, and then the inverse image of closed set is closed, and the image of the closure of a set A is a subset of the closure of f of A. Okay, so this we have several characterizations of a continuous function. Now here is the important things that instead of taking f of closure of A, if we take the interior of A subset of f of A interior, then it may not be a continuous function. So for the continuity, here is the closure, not the interior. So this you keep in mind. The second is here the inverse image of open set is open, inverse image of closed set is closed, but not the image of open set is open, not the image of closed set is closed. So here the inverse image of open set is open, inverse image of closed set is closed. So this is the important. Then the next is that when xn converges to x, implies f of xn converges to f of x, but not the converse. That is to say, f of xn converges to f implies f of xn converges to x. So this is not the case. Okay, and then we have seen several exercises, and we have also seen that here is the function f is continuous if and only if for every set B, inverse image of B, closure of inverse image of B is a subset of inverse image of closure of B. And of course, we prove that the f is continuous if and only if f inverse interior of B is a subset of interior of f inverse B. Not this contains this set, but here is this reverse. So here is the inverse image is containing in this one. Look, here is this is a subset of this one. Okay, and here is this is not a subset of, but this is a subset of this one. So this is the main thing here is, and then several exercises. I am not going to give the proof of these exercises. And then we defined the origin lemma. So before that we defined the separation of two sets by a continuous function, and the Euler never says that A and B two disjoint closed subset of a metric space X, then there exists a continuous function from X to close interval 0, 1 that separates A and B. That is to say, there exists a continuous function from X to close interval 0, 1 such that f of X is equal to 0 when X lies in A and it is equal to 1 when X lies in B. So, that was the original lemma. And then we have proved that the continuous image of compact set is compact, and we have proved that several examples. Okay, so here are several exercises that we have proved that. Now you see, if A is a dense subset of X, then the image is also dense. That is to say, the continuous image of a dense set is dense provided that the function f is bijective. So, here the continuous image of a dense set is dense provided that the function is bijective. If the function is not bijective, then the image of a dense set need not be dense. So, this you have to keep in your mind. And also, if A is a subset nowhere dense set, okay, A is nowhere dense set, then f of A may not be nowhere dense set. Okay, even then the function f is continuous and bijective. So, if A is nowhere dense set, then the image of the continuous image of nowhere dense set is not nowhere dense, even then the function f is bijective. Okay, so this we have proved, and then there are several other exercises that I am not going to, and then we have discussed about the continuity of uniform continuity of a function. Okay, and I am not here is we have already proved that discuss about if the function is uniformly continuous, then it is continuous, but the continuity does not imply the uniform continuity. Now, the question is that under what condition a function, a continuous function can be uniformly continuous. So, the thing is that a continuous function can be uniformly continuous if the function, if the domain set is compact. If the domain set is compact, then every continuous function is uniformly continuous. So, this we have to keep in our mind. Okay, and then if f is uniformly continuous, then f of xn is a Cauchy sequence in X. The image is also a Cauchy sequence in X. So, it is not true for the continuity. If the function is continuous and xn is a Cauchy sequence, then f of xn may not be a Cauchy sequence. But if the function f is uniformly continuous, then the image sequence of a Cauchy sequence is also a Cauchy sequence. So, this is a very important thing. Then several examples, exercises, and then we discussed about the homeomorphism. Homeomorphism is that a function f from a metric space X to Y is a homeomorphism if it is bijective, that is to say 1, 1 and on 2, and the function is continuous and its inverse image is also continuous. And let us recall again the definition of the isometry. So, the function f is isometry if the distance between f of x and f of y with respect to the dy metric is equal to the distance between x and y with respect to the metric x. And then we have several characterization of a homeomorphism, that f is a homeomorphism if and only if image of open set is open, image of closed set is closed. Now, there are two things. For the continuity, the function is continuous if and only if inverse image of open set is open and inverse image of closed set is closed. Okay. So these are the characterization. The function is continuous if and only if inverse image of open set is open. Okay. It is equivalent to say that inverse image of closed set is closed. But for the homeomorphism, because in the homeomorphism the function is 1 1 and onto, and function is continuous and its inverse image is also continuous. So we can say that the function f is homeomorphism if and only if image of open set is open, which is equivalent to the image of closed set is closed. Okay, then there are several properties, several examples, and then we had as an exercise, we have these equivalent conditions of characterization for a homeomorphism. So in the homeomorphism, f is homeomorphism if f of closure of A is equal to closure of f of A. Okay, it is not the subset, it is equal to. So here if the function is homeomorphism, then you have the equality. Similarly, you can replace A closure of A by the interior of A, and even then you have the equality. And also you have the equality if you take the inverse image of closure of B is equal to closure of F inverse B, and so also you can take the interior both the side. Okay. So these are the characterization, and in terms of the characterization of a homeomorphism in terms of the sequence is for every sequence xn and for any point x, the fxn converges to f of x if and only if xn converges to x. Okay. So because we have proved that the xn converges to x implies that f of xn converges to f of x if and only if f is continuous. But here, because the function is homeomorphism, the f inverse is also continuous. So we are taking that f xn converges to f of x if and only if xn converges to x. Okay. So here is the both way is true, and then we had several examples. So again, I am not going to do all these examples, exercises here is, and then we discussed the equivalent matrices. So equivalent matrix, two matrices are said to be equivalent if for every sequence xn and a point x in x, the sequence xn converges to x with respect to d1. Okay, it is equivalent to say that the sequence xn converges to x with respect to the d2. Then d1 and d2, these matrices are called equivalent. Okay, and it is the sufficient condition for an equivalency, because in the several results we have used this type of condition to show that a function is continuous, a set is open with respect to one metric is also open with respect to other metrics, provided that some type of this condition holds good. So here is we have sufficient condition that two matrices are equivalent if and only if there exists constant k1, k2 greater than 0, such that this inequality holds good. So this was the sufficient condition for equivalent matrices. And then we have seen several examples, and you can see that here is several examples. We have all these d1, d2, d infinity, because this condition holds good. So they are all equivalent, and if d is equal to this one and d1 is equal to this one, okay, and then we can see that they are not equivalent to each other. And also here is they are not equivalent to each other, and you may not remember, you might be remembering that with respect to this metric CAB is a complete metric space, but not with respect to this one. Okay, so they should satisfy the similar properties, similar topological properties, okay, if they are equivalent. And then we had and then the uniform convergence of sequence of functions. So we have discussed the uniform convergence of the sequences here. Okay. So let's take this way. and then after that we defined this class space bxy and cxy. Okay, so with this recall, let us come to the our MCQs. That is the main topic of today's talk. So here is I consider here is MCQ. So let us take MCQ is here. Okay. Now the first MCQ is the following: let X be a discrete metric space and Y be a metric space, any metric space. Okay. Then every function f from X to Y is one to one, on to, bijective, continuous. Of course, the only thing is that we are taking here is X is your discrete metric space. Okay. So it is X is discrete metric, X can be anything. So it is not necessary that F must be a one-to-one mapping. So this can, and this cannot be, it is not necessary that F is onto, or the C part is F11 and onto. So these cannot be hold. The third thing is whether this is continuous or not. And because this function, this set, the X is your discrete metric space, and in the discrete metric space, every set is open as well as closed. So if you take any open set in B, okay, you take the inverse of that set in X, which must be a subset of X. Okay, so the subset of X is open because every set in X is open. So it means that the inverse image of open set is open, and therefore the function is continuous. In other words, for example, you have a function f from X to Y. Okay, now let us take B is any open subset, okay, in Y, and then you take the inverse image that is equal to f inverse B. But f inverse B must be a subset of X. But every subset of X, because X is your discrete metric space, so this is your open. So we have taken the open set, arbitrary open set in Y, and we have seen that the inverse image of open set is open, and therefore the function is continuous. So that is the way to prove that, to get the answer of this question. Okay. So here is now let's take the second part, second question, second MCQ. The second MCQ, let X and Y be metric spaces. A function f from X to Y is continuous if and only if f of A in f of closure of A is a subset of closure of f of A for every subset A of X. And you know that we have seen that this is one of the condition, equivalent condition of a continuous function. So f is continuous if and only if this is true. This we have seen that it is also one of the conditions. And but inverse f inverse B closure is a subset of the closure of B inverse. This is not true. But you see that the other way is okay. If you take the other inclusion, other way inclusion, then it is okay. So this is not true. But this is true. We have seen that. And for this case here, instead of closure of this, we can take interior of this, then it is true. So it means that the C is not true, but rest of CDE are true. So f is a continuous function if and only if A, C and D hold. So it means that A, C, D, it means that this. So C, the answer of this question is C. Okay. Now take another question, MCQ. So, to take another MCQ, we are considering X and Y are any two metric spaces and F is a function from X to Y, and we say that a function A from X to Y is continuous if and only if for every sequence xn such that xn converges to x implies that f of xn converges to f of x. And now we know that the function is continuous, then this is true. Okay. And for every sequence xn, we have f of xn converges to x implies xn converges to x. Because the function is continuous, then this is true. Okay, f is continuous if and only if this implication holds, but not this, as we have seen some examples that this is not true. Okay, the second thing is that if a sequence, Cauchy sequence converges, it is not true. The bounded sequence you have, if xn is a bounded sequence, then it is converges, then this is not true. So here is we can say that if xn is a bounded sequence, then f of xn may not converge to f of x. If xn is a Cauchy sequence, then f of xn may not converge to f of x. If f of xn converges to f of x, then x may not converge to x. So the answer is only this one. So this is true. Okay, it means that part A. So here is you can see that which of the following holds. So only A holds. So it means that D is true. Okay, so that is the question, MCQ question related to the sequence and continuous functions. Okay, now let's take some other question, MCQ related to the characterization of a continuous function in terms of open ball and closed ball. So let x and y be metric spaces and f be a function from x to y. Then f of A is open for every open subset A in X. Okay? If f is continuous, then the image of open set is open? No, it is not necessary. Similarly, if A is closed, then the image of closed set is closed? No, it is not necessary. So image of open set is open only when f is homeomorphism. Image of closed set is closed only when f is homeomorphism. So for only continuity, A and B does not hold. Okay. Now what about this one? So f inverse B. So inverse image of open set is open. Okay. Yes, this is true. When the function is continuous, then the inverse image of open set is open. And here is the inverse image of closed set is closed. So f is continuous, then inverse image of closed set is closed. It means that C and D holds. So C and D holds means the C and D holds is common, means that C holds. So the answer is C. So answer is C. Okay. Now take another MCQ. The next MCQ says that let x and y be metric spaces and f is a function from x to y which is bijective and continuous. Now keep in mind the function f is bijective and continuous. Okay, so then consider the following statement. The first one, if A is non-empty dense subset of A, then f of A is dense in Y. Yes, this is true. We have seen that if the function f is continuous and bijective, then the image of dense set is dense. This we have proved. So A is true Now, what about the B? If A is a non-empty dense subset of X, then f of A may not be dense in Y. No, this is not true. First is true. If A is nowhere dense set in X, then f of A is nowhere dense set. No, this is not true. Because we have seen that if A is non-empty nowhere dense set in X, then f of A may not be nowhere dense in Y. Even then the function is continuous and bijective. So this we have seen. So this is not true. Okay. Now what about if A is non-empty nowhere dense set in X, then f of A may not be nowhere dense set in Y. So it means that what? This is true.